Assistant Professor, Department of Biomedical Engineering. Here, today we are going to discuss about relationship between pixels in biomedical image processing. First one, here I have listed some basic relationship between pixels. First one, neighbors of a pixel. Here, we have taken 4 neighbors of P. It denotes n4 of P, which shows x plus 1 comma y. First one. Second one is x minus 1 comma y. Third one is x comma y plus 1. And the fourth one is x comma y minus 1. Here, diagonal neighbors, it's shown n d of p. 4 diagonal neighbors of p. Here we have, first one is x plus 1 comma y plus 1, x plus 1 comma y minus 1, x minus 1 comma y minus 1, and x minus 1 comma y plus 1. Suppose if we are taking 8 neighbors of p, here we have we denote nh of p, and also we have we split into 2 for by 4, n4 of p and n4 of p here. And also in some basic relationship between pixels, we mainly concentrate on adjacency. Here the adjacency which is mentioned in V, it denotes the set of gray level values used to define adjacency. Here we have 4 adjacency and 8 adjacency. Here in 4 adjacency, 2 pixels of P and Q with values from V are 4 adjacency if Q is the value set of N4 of P. In 8 adjacency, 2 pixels of P and Q with values from V are 8 adjacency if Q is in the set of N8 of P. That's it. And in M adjacency, mixed adjacency, 2 pixels of P and Q with values from V are M adjacency if Q is in N4 of P or Q is in N D of P and the set is N4 of P, it is intersect with N4 of Q. Here it has no pixels whose values are from V. Here this diagram, this picture, it shows the arrangement of pixels. Pixels that are in 8 adjacents, it is shown in dash and dashed lines and to the center of the pixel. And also the third picture, it indicates the M adjacency. Okay, here this diagram, it shows an arrangement of pixels, pixels in the 8 adjacent and pixels in M adjacency, and 2 regions that are adjacent if 8 adjacency is used here, and the circle pointers, it is a part of the boundary of the 1 valued pixels only if it is adjacent with 8. It should be in between the region and the background with 8 adjacency only is used here. And the next one, it shows the inner boundary of the 1 valued region. It does not close the path, but it has outer boundary. This outer boundary, it does operations and relationship between pixels. And then we have subset adjacency. Here S1 and S2 are adjacent if some pixel in S1 is adjacent to some pixel in S2. Here we have the main component for the main component, which one is path. A path from P with coordinates x, y to the pixel Q with coordinates S, T. It is a sequence of distinct pixels with coordinates. Here we have a coordinates like x0, y0, x1, y1. It is ends up to xn, yn. Here where x0, y0 it is equal to xy, xn, yn it is equal to s, t. Here the pixels xi, yi and xi minus 1 and yi minus 1 are adjacent here. And also we have a region, boundary and edge. Region is we call R a region of an image if R is connected as set. And in boundary, the boundary of a region R, it is a set of pixels in the region that have 1 or more neighbors that are not in R. And also we have a edge. Here the pixels with the derivative values that exceed a preset threshold here. And we have a distance measures here. We have a Euclidean distance, city block distance and chessboard distance. Here we have formulas for Euclidean, city block and chessboard distance are shown here. And we have a DM distance, the shortest impact between the points. And here this slide, it shows an introduction to mathematical tools which are used in digital image processing. Here we have a linear operation. Here H is said to be linear operator if for any two images f and g and any two scalars a and b. Here the operation, it shows h of af plus bg, it is equal to ah of f plus bh of g. And also we have arithmetic operations also. This example figure, it indicates the addition of images. And we have examples for arithmetic operations, subtraction here. Here the image is an infrared image. And we have digital subtraction for angiography images. First one is our mask image, second one is a live image, and then a third one is a difference between A and B. And the result, the last one is enhanced difference image, which gives the exact results of a digitally processed image. And then we have shading corrections, although here we have examples. Also we have image multiplication. First one is our digital dental X-ray image. Second one is ROI, region of interest, mask for isolating teeth with fillings. And the final one is the multiplication, the product of image A and image B. And also we have set operations here. Also we have complements, original image, and we have an image negative obtained using set complementation, and then union of A and a constant image here. Also we have logical operation. This diagram, it illustrates the logical operations. It involves foreground, that is white pixels. Black represents binary zeros and white binary ones. Here the dashed lines are shown for reference only. They are not part of the result. Here we just differentiate using dashed lines here. And then we have single pixel operations. Here we are using the formula for transformation. S, the output S, it is equal to transformation of Z. Here the intensity transformation function is used to obtain a negative of an 8-bit image. The dashed arrows show the transformation of an arbitrary input intensity value Z0 into its corresponding output value. And also we have a neighborhood operations also. Here local averaging using neighborhood processing, it shows, and the procedure, it is illustrated in A and B for a rectangular neighborhood, and also the Arctic angiogram is discussed in this results. And then we have affine transformations. In this transformations, by using digital image processing, it is possible to obtain identity, scaling, rotation, translation, vertical and horizontal also possible. Here we have different functions to meet up different applications in medical image processing. Also we have inverse mapping applications, and also we have registration, vector operations, formation of a vector from corresponding pixel values in 3 RGB red, green, blue component images. Here we have a component image 3 as blue, component image 2 as green, and component image 1 as red. It is measured in single vector column Z equal to Z1, Z2 and Z3. And then we have image transformations. Here it shows a general approach for operating in the linear transform domain. First we have a spatial domain input f of xy. It is fed into transform t of u comma v. The output of transformation, it is fed into the operation r. Here the operation r, it does some operations based on the application. The result is r of t of u comma v. After that we have an inverse transform. which shows the exact results for the input spatial domain. So it is now it is denoted as g of x comma y. So the input f of x comma y in spatial domain, which is transformed, after that we get g of x comma y in spatial domain. And then in transforms we have Fourier transforms, probabilistic methods, and this we have classifications like low contrast, medium contrast, and high contrast. Like that, the example images are shown here. Thank you.